So I think it's time to start. So as I said, I will say a few words in Serbian now, and then we will continue. So zdravo svima. Drago mi je da postoji ovako veliko interesovanje za današnje predavanje. Ovo predavanje održat će Igor Nodelman ispred kompanije Vroom, a uvodnu reč na početku predavanja daće Ilija Duni, koji je direktor kompanije Vast, koju je Vroom nedavno kupio. To će vam već on bolje objasniti, te njihove odnose. Današnja tema vezana je za distribuirano programiranje, rešavanjem i rešavanje problema koji u tom kontekstu nastaju. Biće reči o odnosima monolitnih i mikroservisnih pristupa kroz programske jezike C++ i Go i meni je jako drago da je ovako veliki odziv danas, bez obzira što je ovo predavanje sa predavačima iz inostranstva i ovo je, da kažem, jedno novo iskustvo za sve, ali nadam se da će dobro sve proći. Zamolit ću vas da nakon predavanja popunite upitnik sa utiscima o predavanju, a takođe biće onaj upitnik standardan vezan za razumevanje samog predavanja koji su za one nagradne poene, tako da ću vam poslati već link na ta dva upitnika kada za to dođe vreme. U oba slučaja naravno odgovarate na srpskom jeziku. Što se tiče pitanja predavaču, možete ih postaviti direktno na engleskom, možete ih postaviti preko četa, možete ih postaviti na srpskom, pa će neko od nas to prevesti, znači nije nikakav problem, bitno je samo da se aktivirate, da pratite i da budete slobodni da postavite pitanje i da iskoristite ovu priliku na najbolji mogući način. Predavač je rekao da preferira da se pitanja postavljaju na kraju, tako da bih vas zamolila onda da zapamtite šta vas interesuje i da postavite pitanja. Da li možda neko sad u ovom trenutku ima neko pitanje ili nešto što bi volao da prokomentariše ili bilo šta? Ako nema, ne vidim da ima, onda now I will say a few words in English so that Igor can also understand us. Hello, Igor, and welcome to the Faculty of Mathematics, University of Belgrade. Thank you for joining us today and for your willingness to share your experience and knowledge with us. As I told you a few minutes ago, this is the first time that we are organizing a lecture in English, and I hope everything goes well. I will now ask Ilya to say a few introductory words, and then you can start with the lecture. Thank you. Ilya, please.
Hvala Milena, čao svima. Hello everybody, thanks for taking the time to join our presentation. My name is Ilya Duni, I'm a director of Vast or Car Story from Belgrade. It's one of the first startups in Serbia, formed in 2005 between Belgrade and San Francisco. We started as a search company for used cars, and over time we collected a large data set of about 2 billion records and 20 billion images. Based on this data, we started building analytics apps for the key players in the auto industry in the United States. One of our customers was Vroom, who decided to buy Vast and Car Story in January 2021, and we are happy to be part of Vroom's family. And I say it's a perfect marriage of great business and technology, and we will be able to change the auto industry together. So I won't take any much longer and give my word to Igor Nodelman, Director of Backend Engineering in Vroom.
Thank you very much. Hi, everyone. Thank you, Milena. Thank you, Ilya. Very excited to be here. Thank you, everyone, for joining. And so let's begin. I'm going to talk with you about microservices and how we use them at Vroom, and also what kind of programming languages we use and why we decided to use them. So let's start with a few sentences about me. Ilya already introduced me, but a little bit about my experience in the last 13 years in the industry. I was mainly working on video-related products, from hardware and DVRs to distributed video streaming systems, and then to enterprise video surveillance systems. And in the last 2 years, been part of Vroom, and changing how people buy cars, at least here in the US. And speaking of that change, I want to give you a few other examples of industries that changed entirely in the last 20, 10, or 5 years. And that's pretty much what Vroom is trying to do to the used car industry in the US. So this picture here is a bookstore, and that's how people used to buy books 20 years ago. You might even have a few of those still in your city, but most people don't go to bookstores anymore. You all know what they do, right? They use Amazon to buy books, and that industry completely changed in the last 20 years. Another good example is this view. I'm having this lecture for you guys here from Manhattan on Broadway, where our office is, and that was a very common scene in the streets of New York City. And we still have a few of those yellow taxi cabs, but sorry, what happened? I can hear myself. Is it okay now?
Someone needs to go on mute.
Yes, someone has. Yep, I think it's okay now. Anyway, so that is a common scene that used to be part of New York City, and now almost no one is using that. You know, the Uber technology changing this industry entirely in the last 5 or 10 years. And something that maybe is more relevant to you guys as students is this picture that probably a year or 2 years ago, you had those kind of lectures in one big auditorium, listening to the lecturer, speaking to people in person. And today, even this lecture right now is happening like that. And that huge revolution changed in the very short period of time. So Vroom is trying to do the same thing, but for the used car industry. And that is a very classic scene, at least in the US market, of how people are buying cars. They go to a car dealership. This picture is from the 70s or 80s, but that never changed. Even today, in our modern days, this is still the case, and this is still the way people buy cars. And that's where Vroom is coming to the picture. And our founders saw that a very primitive industry as a huge business opportunity, and decided to change this industry entirely and to bring this to the e-commerce and to the technology world, where we can do a lot of things that small local car dealerships cannot do. So a little bit about the Vroom business. The information here that I'm sharing with you is public. Vroom is a public company traded on the NASDAQ, and this data is part of the S1 filing for the IPO when Vroom went public. So this data is correct to May last year, when pretty much when the company went on the public market. What's interesting to see here is that the used car business is one of the biggest markets in the US. So there is a huge market share that can be taken, but the companies that are playing in that market are very primitive, and it's a very fragmented market. So there is no big leader that enjoys all this potential. So our founders saw this opportunity and decided to enter this market with technology and innovation and e-commerce, the true e-commerce used car company. And you can see that in the last few years, the company is growing in triple digits. This is very unique situation for small companies or companies that are traded on the NASDAQ. So you can read more on whatever data is available on the internet and in our quarterly earning reports that are publicly available. I wanted to show you a quick video. This is one of our commercials. It's 1 minute long, 30 seconds long. 1 second.
Go to a dealership again. So glad we got it online. Go to Vroom.com, buy a car, and we'll deliver it
think I'm echoing here. Is it better now? Okay, so what happened here? Okay. Sorry about that. I was trying to go to the next slide. Okay, so that is one of our commercials. We also had a commercial on the Super Bowl, and we try to show our customers that we basically take the experience of going to the car dealership, which is very, I would say, interesting and challenging to many people, and move it to something that is completely online, very trustful environment where you know that you can trust whoever you're buying the car from. So how are we doing that from the technology perspective? So we are going to talk a little bit about Vroom's backend, but first a little bit history. That's the kind of like a history of the evolution of software architecture in Italian food approach. So in the times that most of you guys probably weren't even born yet, or were babies in the 90s and even before that, when software engineering was very immature, and the development was very on a small scale, small applications. Most of the software development architecture was something that we call spaghetti code, or spaghetti-oriented architecture. And by that we mean that development was pretty much writing a bunch of functions that would have some kind of logic, and the application would just call one function to another and make those function calls. And when the application was small, it was kind of reasonable and okay, manageable. But once the application started to grow, it created a situation where it was pretty much impossible to manage a large code bases because of the inconsistency and lack of separation and ownership in every aspect of whatever you're trying to work on. So the result was that it was very difficult to manage and work on large code bases. So to solve this problem, the industry went more into more an object-oriented approach with services that are having different modules within those services, and they're separated with layers. So this is the lasagna-oriented architecture. So you still had those big applications, but it was much easier to manage your code, because everything was separated into clear boundaries within usually classes, or depending on the language. So that's the time where C++ and Java and C# became very dominant languages, because they really allowed you to manage a much larger code base in a way that developers would able to have separate ownership on different modules. And the communication between them was the communication between those layers. So that is the lasagna-oriented architecture here. And then later on, that was okay for many years. But as those companies grew, there were new challenges that started to appear with that architecture. And the main one is you had this huge monolithic application, this huge, big lasagna that everything was added into it. And when it was small, it was really manageable. But once the organization starts to grow and you have multiple teams trying to work on the same code base, on the same monolithic application, that became a nightmare. Think about, you have this lasagna and you try to change something in one of the layers, and you try to make it without ruining the other parts of the lasagna. That is a very complicated thing to do. And that's pretty much what happened in the industry, because software was developed, it became more complicated, more involved. You had more teams that were working on the same code, and it became very difficult to deliver new software, to make upgrades, to deliver hotfixes, to deploy. The life cycle of development became very slow. So the efficiency of the teams reduced dramatically over time as they grow. So companies wanted to grow faster, they hire more people, but the result is still very slow organization with this kind of approach. So what the industry, the approach that the industry took to solve this problem is microservices. So that is kind of like the ravioli oriented architecture here. So instead of having your code implemented in those layers, you take every layer from the lasagna and put that in a separate service. So every layer is the ravioli right now. So whenever you have new functionality or you want to make the changes that you need to make in your software, instead of opening up the lasagna and making changes in that layer, you just take a single ravioli. You can replace the ravioli, you can open the ravioli and replace the inside of it without impacting all the other raviolis or all the other layers, and they can live really well together. So that allows teams to scale separately and manage very large and complicated code bases. So that's kind of like the evolution of the software architecture and how we ended up in the need to have microservices in our modern days. So that's a little bit about history. That is a good definition of what microservices is. We'll go into the details in the next few minutes. But in general, it's like I mentioned, microservices architecture is an approach to developing a single application, right? The previous approach was, let's put everything in one monolithic application. The current approach with microservices is, let's take that huge application, break it into small processes, but from functionality perspective, it's exactly the same, right? Whatever this monolith would do, now we're doing the same thing, but with a group of small services instead of one big service. Functionality is exactly the same. The only difference is that every functionality is running on its own process. One key thing that is very important is that every piece of those functionalities are independently deployable. So they're completely decoupled and separated from the other services. That gives us a lot of value. And the other key to have a successful microservices implementation is not to have a centralized management. Because if you have a centralized management, you basically get all the problems that you had with one big monolithic application back. So a combination of a centralized management with microservices is the worst combination that you can do, because you have the complexity of microservices, but you're not getting the benefits of microservices. And we can talk about it a little bit later if we have more time. So we kind of touched on that, but this a little bit more into details, when and why to use microservices. So the first item here is the most important one, especially for us at Vroom, as we have a very large team of developers and multiple teams. The fact that we can have different teams own a certain piece of the business, and they are fully able to own this and implement everything they need without having dependencies on other teams and without considering dependencies and having coupled themselves with other teams, allows us to be a big tech company, but move fast as if we are a small startup with 3 developers. So a small team with 3-4 developers can move really fast on a certain aspect of the business without thinking too much how whatever they do might break or impact other teams. And this is the key. And this is the biggest benefit of microservices, at least for organizations that grow quickly and have multiple teams trying to work on the same aspects of the business without stepping on each other's toes. Other things that are, I would say, for us at least, is a second importance, but for other organizations that can be the most important thing, is the ability to scale in different way. When you have different applications, small applications, you can scale them differently depending on their need. This kind of architecture also increases your stability and resiliency of the system, because if your huge monolithic application goes down, all the system is down, versus if few services are down, only a small portion of your a big application is down. For example, if the ordering service is down, in that case, customers won't be able to place orders, but everything else will still function and work. So your way to the way to create a better stability is improved with microservices. Faster time to market, we talked about that. Testability and CI/CD, I won't go too much into details down because we are short of time, but you can read more about that offline. Another very important advantage of microservices is your ability to choose different technologies and to use the right tool for the right problem. Instead of having everything in one application, you are kind of coupled with the technologies that you use. You have to use the same database in many cases. You use the same programming language. You use the same tools, and you have to solve so many different problems. So that doesn't make sense in many cases. So with the microservices, you can have different tools and different applications using different technologies that are most suitable to solve the problem that that specific application is trying to solve. So you can use one type of database, for example, for write-heavy operations that is very good for that, for example, like Cassandra, but you can use a completely different database in a different use case when you need structured data and you don't care about so many reads, but you need more structured data and consistency in your in that application. So you can mix and match. You can use different languages. And another thing that is very important for us at Vroom is you are able to experiment. You are able to try something different that maybe in the future will help you to be more efficient and solve your problems in a better way. So technology diversity is also one of the keys that a key reason why microservices are very popular. Of course, there is also many reasons why and when not to use microservices. I wrote here the three that I think that are the main reasons. There are many others, and in the last I would say 2-3 years, there is a lot of discussions why microservices are awful and terrible, and the industry is trying to go back to the different approach. And that is something that is always happening in software engineering. There are a lot of trends, and the industry is going to one direction and then to another. There is no right answer. The right answer is always what is good for the company that you're working for, or what is the right solution for the problems that you have in your company, right? So I see many companies go to microservices just because everyone is doing microservices. That is a terrible reason to do microservices. There are many reasons why microservices will create more complexity and damage than good. So it's not always the solution, definitely not a silver bullet that you always have to use. And unfortunately, many companies are making that mistake because they think that it will solve all their problems. And in many cases, it will create new problems that they are not even aware of. So few of those is, first of all, the complexity. We talked a little bit about the fact that microservices are it's a distributed system, right? It's a group of services that need to communicate with each other instead of having a simple function call. So the complexity is increased, and also the overhead to develop a new feature or new works can be much higher. So think about a situation where in a monolithic application you wrote a class and now someone can just call a function or use this class, and it's literally a few minutes of work. Here in a microservices environment, you want to write a new microservice, you need to deploy a new service, you need to write a new interface, then another application will need to consume those APIs, learn those APIs, and you need to think about situations that what happens if that service is down, what happens if this service is overloaded. All of those complexities that you have in distributed systems are introduced. So that is something that needs to be considered. Do I need that extra complexity? Maybe the simple approach is good enough for my application. In many cases, it is, and then that is not the best approach. Another thing to consider, and it's also kind of connected to the complexity, is the eventual consistency. As by definition, when you have distributed systems and every system has its own data stores, the consistency of the data cannot be done in one transaction. So whenever something is changing in the system, it's going to change in one place, and it will take a few milliseconds or seconds or sometimes minutes until that data is propagated to all of the other entities and the other nodes in the system. So that is another layer of complexity that is added with microservices that needs to be considered, and a lot of edge cases and problems that need to be considered from software engineering perspective. Sometimes it is okay to have eventual consistency. Sometimes it can create a huge problem if the customer doesn't see the latest information wherever they are accessing the data. So all of those new problems are introduced with this kind of architecture. And the last one here, which is also very important, it's last but definitely not the least important, is the complexity of everything related to the operation of those microservices. So deploying the microservices, managing them, knowing how many you have, where they are deployed, and debugging issues, looking at logs, understanding the utilization of different operation system metrics like memory, CPU, networking on dozens, hundreds, and sometimes thousands of services that are running. It's a very complicated situation. Think about a situation of trying to debug a problem in your system. When it's a one big application, it's relatively easy. You know where to look for the issue. There is one set of logs. There is one set of code, and you just figure out the problem by looking at the same place. With this kind of architecture, it's very difficult to even know where to start looking for the problem. And then you have multiple instances of every application. So the complexity of debugging and the general operation is very high. And sometimes it's not worthwhile to go through all this complexity if you don't need that. So you really need to understand what value microservices gives you before you decide to use microservices. So we'll talk a little bit about scaling. This is just a visual illustration of how different it is to scale an application that is on the left side. You see the monolithic applications that have different functionalities in them. And when you want to scale that application, you create multiple instances of that application. And then you just scale by duplicating the entire application. With microservices, you can pick and choose. You can scale one application, but not necessarily you have to scale the other. And that gives you a lot of flexibility with scaling. You can horizontally scale the specific application and be much more efficient with resource utilization this way. So is microservices always the right choice? I think you already know the answer based on what we talked about so far. Absolutely not. So let's talk a little bit about microservices in Vroom. So far, we talked about microservices in general. So you see this picture here of this huge graph and different nodes and the connections between them. That is a real example of Uber's backend microservices topology. Uber has, the last article they published, 2,200 microservices running in their backend, and that is how they're connected. It's really interesting to see, and it's a good illustration of the complexity. And Uber is one of those companies in the industry that is using microservices intensively. It solves a lot of problems for them, but it also creates a lot of challenges for them. And they talk about those challenges a lot. So I think I got disconnected. Can you guys still hear me?
Yep.
Yes, we do.
Yes.
Okay, great. I'm moving to the next slide. So this slide is a very high level overview of Vroom's backend. So let's go from the top. Oh, I have my laser here. That's great. So here on the top, we have our clients. Our clients can be the web application, the mobile application, or some third party that is consuming data from Vroom's backend. The the backend is running here in this big blue box, which represents our Kubernetes cluster. And the Kubernetes cluster is managing multiple Docker container images. And those Docker containers are basically our Go microservices applications. So we have multiple applications, as you can see, they're running inside Kubernetes. Each one of them has its own data store. For example, most of them are using Postgres, some of them are using Elasticsearch, some are using Redis. It really depends on the need of the application, like we talked before, that every application might need different tools to achieve what it needs to achieve. So the result is that we select the technology that we need to achieve those goals. And we use here GraphQL interface to interface our clients to our backend. We'll talk a little bit about that in the next few slides. And we also use Kafka as our messaging system to communicate in an asynchronous way between the services. That is a very high-level overview. So let's talk a little bit about a few challenges that we had while transitioning into microservices at Vroom with time. So one of them was APIs. I mentioned GraphQL here on the top, but that wasn't our original architecture when we started with microservices. When we started, it looked more like this. So we had our services running in the Kubernetes cluster, but our applications didn't have the GraphQL layer that you saw in the current architecture. So the result was that our mobile developers or web developers, to consume data from the backend, they would have to make multiple calls to be able to get the data that they need, because every service would be responsible for a different aspect. Like you would have one service that would do account management, another service that would do car search results, another service that would do something that is related to the transaction of buying a car and ordering cars. So in order to present a page to the user on the website, the web application would have to make 3, 4, or 5, or even 6 in worst case scenarios, different calls to the backend to be able to present to one page. So that adds a lot of complexity on the web development side, first of all, and second of all, very inefficient, especially if you're on a cellular network, because then it might be very slow. And if you have to make 5 separate calls, it would take a lot of time for the application to load. So to solve this problem, we introduced GraphQL, like you saw here in that slide. So the way GraphQL works, I'm not going to go too much into details, but it basically kind of like an API gateway or a centralized interface where the clients can make a call to that centralized interface, and that centralized service will make all the calls to all of the services, aggregate the data, and send one result to the client. So this is a good illustration of this, and it also shows the evolution of API architectures in general, from monolithical applications to what we have today with microservices. So the first generation is here on the top left. This is the huge black monolithic application here. And in the good old days, it was really easy. The mobile applications or the web applications would just make a call to that monolith. You get the result, no problem, very easy. Then once the industry went to microservices, which we have here on the bottom, that is exactly the problem that I just described, right? Like you have all those different clients and they have to make so many calls to get the data that they need. It added a lot of complexity on the client side suddenly. So the industry is trying to solve this problem by introducing some kind of layer in between here. This is in our case, it's a GraphQL, but you can use any other technology to kind of centralize this interface. So a centralized layer for interfacing between the client applications to the backend. And then that layer is doing all the heavy lifting of calling the different services and collecting the information that the client needs. That solves a lot of problems, especially related to performance, but also reduces the complexity on the application side and moving the complexity to that centralized location. But this is not perfect. If you remember the definition of microservices, one of the key aspects there is that it is very bad practice to have a centralized management location of anything. That kind of breaks the microservices advantages. And that's exactly what happens here. Because if you have this huge centralized interface layer, it means that every developer that is working on one of those microservices, when they are done with whatever they are done and they want to expose something on outside some new API, they have to work on this layer to expose that API. So the result is you have this one big monolith, right? But instead of being this monolith inside the application, you have a monolith API layer, which is kind of a compromise, right? It's not as bad as having the entire thing in one application, but if you grow to a very big size like Netflix, those images are, by the way, from a Netflix tech blog referenced here at the bottom. So that created the problem for Netflix because they have huge organization, and when you have a lot of people, they all have to touch this layer, and they kind of went back to the problems of having this monolithic application. So the solution for that is, and that's something that we at Vroom are looking into adopting that, because we are starting to have this problem too, given the size of the tech organization, is to have something called federated gateway, which is another layer. Like always in software, when we have a problem, we solve it by adding another layer. This is yet another example for that. It is always the solution. So you add another layer, and then you have like a group of microservices that have their own GraphQL interface, and then you have a federated GraphQL interface that dynamically detects all the changes in the smaller GraphQL entities and then exposes them to the clients. It's a little bit more complicated. I'm not going to go into details, but if you want to read about that, there is a good reference here at the bottom. It's called GraphQL Federation. Move your time. I'm going to go quickly because we don't have much more time. Another challenge that we had is shared databases. So we did probably one of the big mistakes you can do when doing microservices is to use a shared database for all services, and that goes back again to the same problem with the GraphQL, with the big GraphQL layer, and breaking again the same rule of microservices. You don't want to have one centralized management entity. And if you have one database and multiple services talking to the same database, then you kind of enjoy, you suffer from the problems of microservices, which is the added complexity, but you don't enjoy the benefits if you have this centralized database, because then you still have the same problems of one team is trying to make a change, they need to update the database, another team is doing the same thing, and then one team wants to release their update to the database, but they can't because another team is still not ready and they have their changes already implemented on the database. So you have to separate them and cherry pick changes. So that adds a lot of complexity on the collaboration between teams. That is one problem. Another problem is scalability. You might need a different scale for the database for different services, and because they are all sharing the same database, they have to scale in the same way, although that some of them not necessarily need that scale, so very inefficient. So scalability is an issue. And also, as I always say, like, you have to use the right tool for the right problem. If you have one database for all services, you have one tool and you have to solve all your problems with that tool. And today we have hundreds of different databases. Every database is trying to solve a different niche, a different problem. So using one database to solve all the problems is very, I would say, not very up-to-date way to approach software engineering. So that's something that we had to go through and break our database to small databases and have a database per service. 5 more minutes, but Milana, I can have another 10 minutes extra, right? So I'll
yes,
go a little bit.
sure.
Okay.
Sure.
So
Take your time, please, because the students sometimes complain that I should have given lecturer more time. So please take your time. I don't want them to complain this time too. Okay, just
Okay,
take
okay.
as much time as you need.
Okay, I don't want them to complain. So yeah, absolutely. I'll take 10 more minutes or so. We'll see how it goes. Another challenge that I wanted to discuss is that's something that happens a lot. Once you guys start to work in real companies, you will see that today in software engineering, it's not only developing, but also a lot of work with third parties, integration. That is something that is fundamental to any company today. And sometimes those, and always those third parties, you don't have control on them, right? You don't know a lot about them, and they usually disappoint you in terms of their stability, their reliability, their performance. And the biggest problem with that is you don't have much control, right? Like you can't go and fix their problems. They have their own priorities. In many cases, they don't really listen to what you say. So the reality is you need to find a way to manage this situation well and handle this situation. So how are we doing that? Different approaches. One of them is retries mechanisms, throttling mechanisms, and eventual consistency that we discussed a little bit before. And we use Kafka, as I mentioned before, and Kafka is helping us a lot with all of those three things. I will explain a little bit more in the next slide. So yeah, I kind of ruined this slide because I already said Kafka. I wanted you guys to guess what this means. It's Apache Kafka. So I'll skip that slide as well. So message queuing. Message queuing is another key aspect of modern microservices architecture, although it wasn't there in the definition, because you can have microservices without message queuing, but it won't be fully used at its max capacity or its max ability if you're not going to introduce message queuing as part of your microservices ecosystem. And we use at Vroom Kafka, as I mentioned. And basically, if you don't know what the message queuing is, this slide illustrates that well. It allows you to decouple services really well and reduce dependencies. So one service, one microservice doesn't have to know anything about the other microservice, but they can still communicate with each other. And that is how it is done with the queuing system. So basically, a service can publish information about something that happened. For example, a user signed into the website. So a message is being pushed into a queue by the service that is responsible for user management, that there is a new user that is signed up right now, and the message is going to be added. So you can have a queue of messages that will represent every sign in or sign up to the website. Now, you might have another service that is interested about this information, and then as a result, let's say, send a welcome email to that user, right? That can be a different service that is responsible for marketing and email communication to customers. So without message queuing, what you would do is that user service would have to call with some interface to that marketing service and say, there is a new user that signed up, here is the information, and then that application will go and send the email. So you create a coupling between those services. They have to know a lot about each other, and they also start to be very dependent one on the other in terms of scalability, right? Because let's say you have a spike in the number of users that are registering to the website, so you increase the number of microservices that are responsible for that. You also have to increase the number of services that are responsible for sending those emails, because then they won't be able to handle the load of the communication that is starting to make those thousands of or whatever number of calls to that application. So with queuing, you kind of solve this problem, and your one benefit is the decoupling between the services. So a service can publish information about a certain event, and then you can have multiple services that might be interested in that data. Any one of them can register for notifications on that kind of event, on that topic, and do whatever they want. So if in the future you want to do something else as a result of the sign-in event, let's say you want, besides sending the email, you want to also send them a t-shirt, right? So you want another service. You don't have to change anything in the sign-in in the account management service. All you have to do is to write a new service, register to the same message queue, and then listen to those notifications and then handle them, right? So there is a good separation between the services, and separation is very important because then every team that owns a certain aspect, then they can work independently without thinking too much about other teams and how they impact other teams, because there is very little dependencies and coupling between those services. So message queue is very important for that aspect. And again, I kind of touched on that also for scalability and handling services that are a little bit slow or need retries. So think about a situation where we need to call a third party, and that third party is unreliable or slow. We can have all the messages that we need to send to that third party waiting in our queue in Kafka or whatever technology you use, and you can consume those messages in a slow way, in a way that the third party will be able to handle those messages and throttle the number of messages you send to that slow third party. Or if it fails or goes down, you can retry the messages until that system is back up. So it gives you a lot of flexibility and resiliency and solves a lot of high availability problems with this kind of approach. You can recover from issues much better. Also, if one service goes down, one of your service goes down, and while it is down, you're not losing data, right? Because the data is still waiting in the queue. Once the service is recovering, it goes up, it connects to the message queuing system and consumes all the messages. So that's why we talked about eventual consistency. The service can be down and still no data is lost. It will eventually get into a consistency mode where everything is functioning correctly. So this kind of flexibility is crucial in a modern microservices architecture. So a message queuing bus with a pub/sub or whatever other architecture is very important in every microservice architecture. And that helped us to handle different third parties that were not very reliable, and also sometimes failures within our own system. Okay, so we talked a lot about microservices. Let's touch a few minutes on Go. I want to show you that video. That should be fun for you guys, hopefully. So this is the breakdown of the most popular languages since 1965 to 2021. And the reason I want to show you this because I think you guys will be surprised with how many changes have been happening in the last 40 years in the industry. Like if you look at this is now the 70s, all of those languages that you see here, you probably didn't hear about them or definitely never wrote in any of those languages. And you see that they're super popular in the 70s, and then we will enter the 80s, and it's still very different than the way it is today. And the reason I want to show you this is just to emphasize how much the industry is changing all the time, and whatever is the most popular today, it's going to be very unpopular very soon. It's for sure. There is no question about it. Like, who is using ADA today? Nobody. But at the late 80s, that was the most popular language. So you can see C is dominating the 80s, and at around the beginning of the 90s, where object-oriented started to pop up, you see that C++ is catching up, and soon probably Java and C# will show up. So this is an interesting time around the 90s where the internet started to appear. And with the internet, you had JavaScript and Perl and PHP will soon start to take over the world pretty much. So yeah, you see that during this time, basically, Java is the king of the backend, JavaScript and PHP is the king of the internet. And now as the internet is growing and the web is growing, those applications will start to take over and become bigger than Java and the backend. So PHP was huge not very long ago. Now PHP is kind of like, nobody wants to touch PHP. It's kind of like a nightmare to work on PHP right now, but it was not very long ago one of the most popular languages. You see that C# is getting stronger, and Python, look at Python. Python has a strong finish here. And yeah, we're approaching the end. There we go. And yep, just in the finish line, Python is #1 right now. So yeah, you can really see that the current state is that Python and Java are dominating. Python is used a lot to write web applications for the backend, for modern web application, also for machine learning and data science. So Python becomes very strong language, and JavaScript, of course, on the web side, which is a historical mistake, but that's probably something we can talk about for an hour separately about JavaScript. So the reason I'm showing you this, and I don't know if you noticed, Go wasn't on that list, but it doesn't mean that Go is the wrong choice. On the contrary, I think that in 5 years this will look completely different, and Go will be somewhere on the top there, replacing Python and Java as the leading language for backend. What's happening? Second. Okay, so is there, can you guys see my screen? Yes, I think now I'm back. So the question that comes up from this is, what is the best programming language? So, and as I mentioned multiple times during today's session, is there is no such thing as best programming language. There is no such thing as best architecture or best database. It's really using the right tool for the right job. And Go is born from the situation of that the tools that we have right now weren't good enough for the modern microservices development style, right? And that's the reason why Google decided to develop this language. It's kind of like an alternative to whatever we had right now in the industry to solve all the problems that we have with the existing languages that were developed for the era of the 80s and the 90s and are not aligned with the modern architecture. So the main thing are the current era is the multi-core Dockerized microservices architecture, and Java and C# are not a good fit for that because they have a very large runtime and they're very inefficient to run in that kind of environment. So the alternative was to go to C++, but C++ has its own problems with the complexity of developing in C++. So Go was kind of a compromise of making a language that is like C++, but without the complexity of the memory management and the syntax and everything that means. I think you guys use C++ during school, so you probably know what I'm talking about. So that was the motivation in Google why to develop Go. It's a relatively new language, but it's catching up very quickly, and I would expect that in 5 years it would be on the top of the list. And that is why we at Vroom decided to use Go. I kind of mentioned some of that that is here. It's very small, very simple. It's easy to read. It has a very small runtime. It's very fast. It's almost as fast as C++ and much faster than the other popular backend languages. Yeah, I have a chart here that shows you that Go is pretty much in the same speed. Here it's #1. I don't think it's, I think C and C++ is a little bit faster than Go, but I don't know who did that test. But it's not really important if it's 1% slower or faster, as long as it's on the top. And if you compare it to Java and C# and Python and languages like that, it's significantly faster. So the result is that today in the cloud environments where you think about the cost of deploying all those services into the cloud, and you have to pay for every machine that you run, for every CPU usage, for every memory, that is a very important aspect of having small applications that are very efficient that save a lot of cost for the company. And you can do a lot with very small application. And now that your applications are small and they're microservices, Go is a perfect fit for that. And yes, we touched a little bit that Go is very strong on concurrency, and in today's world, machines are having large number of cores, and Go is probably the best language to utilize all those cores in the most efficient ways because of the green threads, which is a kind of a new approach to threading and concurrency that I think Java is just adding it now to the latest version, if they didn't already. Let's move on because we are really short on time. We touched on low cost for cloud applications. We don't have to talk too much about interoperability, but it kind of like gives you a fallback in case of if there is anything that you need to use that you don't find in Go. You can always link Go with classic C application and execute C code from Go. So it gives you a flexibility to reuse existing code if you have any that is too much work to port into Go. A few examples of other companies and other famous technologies that are written in Go. So yeah, Google's backend is written in Go, which is a big testimony of what it can do. Uber, Dropbox are also using Go for their backend. Docker and container are written in Go. Some famous databases and other operation systems like Fedora and whatever you see here on the list. There are many other companies that are using Go right now, and the community is very strong as well. So Go is the current king in the backend software engineering, and that's why I have this image of the gopher with the crown. And that is the last slide before we finish. As you could see, that it was very high level, introduction level lecture. And I encourage you to click on those links here or buy this book that has much more details. And feel free to ask any questions that you have now if we have any time.
Thank you, Igor.
Thank you.
Just before we move to the question sections, I want to paste a link in the chat section. We are hiring both for Vroom and Car Story, and you have the link with all the positions. I guess your students, Milena, will be most interested for the junior backend role, which we have both for Vroom and Car Story, and also pasted links for Igor and me. I encourage everyone to ping us if you have any questions. Milena will have these slides later for you. We will add these addresses to the slides, and let's move to the questions. Thank you.
Okay, thank you, Ilya. Thank you, Igor, very much for this inspiring lecture. I will now ask first if there are some questions. Usually there are questions, but they're a bit shy to start. But I hope that now they will not be shy.
No problem. And if someone wants to ask something later, that's also an option. Send an email or ping us on LinkedIn.
Yeah, but I think it should be nice to have some questions now. This was really inspiring. I would just say we started teaching Go 2 years ago at our course at the university. It was like something that I thought it would be good for students. So I now really enjoyed everything you said, and that confirmed my choice about teaching Go at one class. Not all of these students are learning Go at their classes, but that might change in the future. And yeah, I would also mention that this video you showed us about most popular programming languages, it is also something that we watch at our first class when we start this course. So it's all we actually watched another one that is not, it is a bit different, but the same kind of movie. So it was nice to hear your impressions about that and your comments. I would like to ask you to begin questions. So usually I begin with questions and then students.
Okay.
I would like to ask you, so you have very interesting. You were born in Russia, then you moved to one place to another place, finished studies, working everywhere. So it is something that shows that in this job you can actually work at different places and be at different places. I would like you to share your experience about that, because I guess there are many people here who are considering working abroad or moving or things like that. So it is always nice to hear experience.
Yeah, sure. So just like yeah, so I was born in Minsk in Belarus in '84, and then at 1990 my family moved to Israel. So most of my life I spent in Israel. So I lived there until 4 years ago when the company that I worked for relocated me to New York, and then 2 years ago I left them and joined Vroom. So yeah, I did like two big relocations in my life, but I think in our industry it doesn't matter like where you're located, as long as you can speak the language, and English is kind of like the international language, especially in our industry. You can work from everywhere. Like we just had this conversation with Ilya before about like hiring people in different places, and as long as you have Wi-Fi today, that's all you need. You can be on the moon, and if you have Wi-Fi on the moon, you can work for every company you want, because everyone is accepting the concept of being remote right now, especially with COVID. And yeah, I'm in the office right now with Ilya here in New York, and we are the only people in the office. We just came here to meet each other because the first time I see Ilya face to face. But I don't think that even after COVID is over, we will still come to the office in the same way. So the reality is definitely changing, and it's changed. So it makes it even more flexible to be anywhere you want and do whatever you want, at least in our industry, right? Like it doesn't work for everything. It's not going to work for doctors or nurses in the hospital or for taxi drivers. That's not going to change. At least they will physically have to be there. But in our industry, absolutely.
Okay, thank you. Okay, now we have some questions. You can read it in the chat. So, from your experience, are there any features that Go is missing that you wished it had? Any typical mistakes that novice Go programmers make when building backends?
Great question. Great question. So yeah, obviously nothing is perfect, and every language has advantages and disadvantages. The biggest complaint that people that start working on Go have, that usually that they are coming from other languages like Java or C#, is that Go doesn't have generics, and that creates a situation where people have to copy paste a lot of code to do whatever they used to do in a generic way. Or like with templates in C# and C++. So there is a lot of discussion about adding that to Go, and Go 2.0 will probably have generics. My personal opinion is I would prefer that not to be added, because one of the biggest benefits that I see in Go is the fact that it's simple, and sometimes, yeah, you have to write more code, but the modern approach is that writing more code is not a problem. Writing more code is good. If the code is very readable, that's more important, to keep the code readable than to have something done in 2 lines of code, but then nobody can understand what is written there. There is no pride in having small, short functions anymore like it used to be in the past, right? You can take pride in something that can be very long, but a product manager can look at the code and kind of understand what's going on. That is much more respectful and a much better piece of code than something that, you know, oh, there is some magic trick, you can do something in generic way, and you really need to understand the complexity of the system to read the code. So there is a trade-off there. And one of the biggest benefits of Go that it is simple, and there is one way to do things. It's very readable. So having to add that complexity to answer some needs or some features that other languages have will kind of over time will bring Go back to the same problems that other languages have. So I'm kind of hoping that it will not happen, but I have a feeling that it will, at least on the generics part.
Okay, thank you. There is another question. Does the message queue ever crash? It seemed like a very, very important part of the architecture, but I only saw a single instance.
Great question. Again, very good question. So first of all, everything crashes. You have to take this assumption, right? Everything crashes. Even if the software doesn't crash, the hardware crashes, right? And absolutely, message queues are crashing, but a good message queue system like Kafka is solving this problem in a high availability distributed approach. So in that image that I had, it was a very simplified way to show how Kafka works. It is not like that in reality. In reality, in a Kafka cluster, you have multiple machines, and every topic, which is kind of like a subject when you write messages into, has replication factor of whatever you want. Usually, most people use 3 replication factors. So every message that you write is duplicated in another 2 machines that, if you're using cloud environment, they can be deployed in a different availability zone or even a different region in different sides of the country or different continents. So that message queue system, again, Kafka as an example, will tolerate a failure of one or 2 machines. Let's say you have a replication factor of 3 and 2 of your machines are down. There is something that is called a zookeeper, which will manage the leader of every topic. So once one leader is down, another leader will be automatically elected. I don't know if you guys are learning about leader election in the distribution system courses that you might have, but there's something very important as part of a good distribution system is to talk about leader election and to handle high availability and failure situations. So yes, nodes and brokers can go down, but a modern and a good messaging system will be able to tolerate partial failures, and the clients that are using those systems shouldn't feel much impact unless everything is down. Yeah, that's a great question.
Okay, thank you. Do we have some other question? You can also ask in Serbian. We can translate. Okay, there is another question. What problems did you encounter while building microservice architecture?
Okay, yeah, that's good. I mean, I think we kind of touched on few of them during the session, but I can give another example and kind of to demonstrate the complexity of monitoring the services. So we use Datadog to help us with that. Datadog is a centralized cloud system that you can push all the information from your services into that system. By information, I mean metrics, logs, and it will create it's kind of like our ears and eyes on the system. So in every moment, every given time, we can see exactly what's going on in all of our services and have a lot of information about failures, errors. So it gives us a great visibility, and we can detect issues in a very short period of time thanks to Datadog. I encourage you guys to look into Datadog. Just Google Datadog and see what they have to offer. How many microservices Vroom has? Around 50.
Okay.
But that's a tricky question, right? Like, because every service can also have multiple instances, right? So you can have 50 microservices, but every service may have 200 instances of that service, right? So I don't know how many instances are running. It's really dynamic, and we are changing. It depends on the load. For example, during the Super Bowl, we scaled the system in a very strong, aggressive way. So it's kind of dynamic and changing depending on what's going on. So yeah. What was your area of interest before microservices? So I'll answer that. So definitely video. If you saw the previous companies that I worked for, all of them were related to video in one way or another. So video encoding, video decoding, video processing, video streaming. everything, especially the streaming part and the network part of streaming the video was something that I was focusing on a lot before I joined Vroom. Different streaming protocols, more low-level stuff, more in C++ than in any other language. How many people are working at Vroom? Around 1,000 altogether. Before, not including VAST, I think with VAST probably another 100 people, something like that. Have experience with? No, I don't have experience with those.
Okay, please read the question because it will not be on the video.
So someone is asking if I have experience with Erlang. So no, and I don't even know what is Elixir.
Elixir. Yeah,
no idea. No.
Okay, these are functional programming languages, also built for concurrency and for backend, getting more and more popular, especially in functional language communities. So, yeah. Let's see another question. How many engineers are working in Vroom? I think we already answered that question.
So 1,000 is altogether, around 1,000 employees. How many of those are engineers? I think around 100 at Vroom and another 80 at VAST, something like that, but I don't know exactly.
About 35 at VAST.
Okay. So I think around 150 altogether, something like that.
Okay. How do you ensure the application has good performance? The amount of requests seems to be very large, so it seems to me the delays would be very high.
Well, yeah, so how do we ensure? We basically do a lot of load tests on the system. We run tests all the time, continuously, and part of those tests are functional verification that things are working correctly, but part of the tests are also performance testing. So if something, if a new code was added that is creating a regression in the performance, then we address this issue, and we spend a lot of time optimizing our systems so they will perform in a very high scale, considering that we need to be able to support huge events. Like I think I mentioned that a few times, the commercial that we had on the Super Bowl. It's the biggest event in the US with more than 100 million of people watching that, and we had the commercial during that event. So the result is a huge spike in a very short period of time. So testing is key, not only for performance, but for everything else. And I have like 2 more minutes. So guys, maybe last question if there is any.
Okay. Any other question? I think we should thank Igor very much for his lecture and for all the answers and all the time he spent with us. And yes, if someone has questions, can write some email or you have this contact address. So thank you one more time and hope to see you again. Yes, I will now skip to Serbian to give some messages to students and yeah.
Thank you very much. It was a pleasure.
Thank you.
Bye-bye.
Ok, mi sada nastavljamo, znači sad ću vam podeliti